Good morning. Welcome to the final press conference of this year's EGU General Assembly. The topic is air quality and urban air pollution, and I'll remind everyone for the last time in this meeting that we'll open the floor for questions following short presentations from the speakers. Both those journalists here in the room and those watching us remotely are welcome to ask questions. Those watching us online can do so by messaging EGU.media on Skype or by using the Twitter hashtag AskEGU. I'll now introduce our speakers. The first one is Augustin Collet, who is a researcher at INERIS, the French National Institute for Industrial Environment and Risks. Jorgen Brandt, who is head of section and senior scientist at Aarhus University in Denmark. And Vasiliki Asimakopoulos, who is senior researcher at the Institute for Environmental Research and Sustainable Development at the National Observatory of Athens. And I apologize that the affiliation is wrong in the handouts you received. This is the correct one. I'll now hand over to our speakers. Thank you.
Hello, so I will introduce the results of a French project we had that investigated European air quality at the Horizon 2050, looking at the impacts of climate change. The scope is to try to understand to what extent air quality policies that are being planned and enforced now will remain valid in the future under the combined pressure of climate and long-range transport. We know that there's a penalty that is bearing upon ozone pollution specifically because of the impact of global warming and heat wave frequency on ozone pollution events. For the impact of climate and particulate pollution, it's more uncertain. And last, we know also that there's a penalty that is brought about by long-range transport on air quality. Now, we don't know exactly to what extent all these factors compete with one another, and we need to inform to the policymakers to tell them if the current air quality legislation will remain valid in the future. For ozone, I mean, it's split between ozone and particulate matter because it's occurring in a slightly different way. But for ozone, we confirm the climate penalty. We find a major influence of long-range transport, and we conclude that the air quality legislation remains efficient despite these penalties. For particulate matter, the climate impact is not so clear, but we still confirm that the air quality legislation dominates. So as scientists, I conclude that we should support the air quality legislation that is being planned today if it happens to be efficiently implemented. A bit more details on the methodology. So we use a set of different scenarios, prospective scenarios. It's the same as the one used in the IPCC process for radiative forcing and climate forcers. But for air pollution, we use a revised set that actually builds upon the global energy assessment and includes explicit handling of air quality measures. All these emission sets are then fed into full-frame geophysical models. So it's quite a comprehensive set of modeling that we have here. We have a global climate model, one of the IPCC model, basically. We have a global chemistry model. It's one of the atmospheric composition change model intercomparison project, again, an international experiment. These global models are then downscaled at the regional scale with a regional climate model. It's the CORDEX experiment, for those who know it. And then all these fields are fed into ultimately the chemistry transport model that also use the air pollution emissions and the global chemistry as a forcing at the boundaries. So here the key message is that really the major effort was done on putting together all these very complex models to try to find out what is the future air quality in Europe. What we find here, I'm just showing for one of the pathways that is relatively pessimistic. It has no climate policy, so we expect the greenhouse gases emissions to increase up to 2050, but it has air quality legislation. What we find is that there's still an increase of ozone. If we compare to the current situation, you have a mild increase, but there are quite a few areas in Europe where this increase is not significant. That's why you have white areas on this map. So it's interesting to know what the future would look like, but the most interesting is to know why. And we're doing a decomposition analysis, reproducing the whole modeling chain I showed before, to isolate the different factors. And we have here the overall response, the same as I showed before, a mild increase, penalty of pollution, and we actually find that this is due to a climate penalty. So we confirm the impact of climate on heat waves and then ozone. That is compensated by a sharp decrease attributed to emissions. That's the good sign, saying that the air quality legislation is efficient. and a major penalty of the background that is actually exceeding the penalty of the climate. That's for ozone, and then for particulate matter, if you compare the future and the current, there's actually a very sharp decrease according to this scenario. So actually good sign particulate matter pollution will decrease in the future. And why is it so? Here the picture is a bit simpler because background and climate have actually limited impact, and it's really attributed to air pollutant emission changes. So to sum up, again, as scientists, we're happy because we developed what we consider a really comprehensive set of geophysical models. We're using the last generation projection pathways to offer something that is policy relevant. And we conclude that the currently planned air quality legislation is useful, even if the context is not so favorable. And we also highlight the fact that for long-range transport, air pollution will bear upon ozone pollution levels, and international mitigation should be sought after. There's also a message for scientists, is that we don't have really a strong, robust understanding of the impact of climate change on particulate pollution, and that needs more investigation in the future.
Okay. The next one. Press this icon down there. Okay, so my name is Jørgen Brandt, and I'm coming from the University of Aarhus in Denmark, Department of Environmental Science. And I'm going to present some results for you from a very comprehensive integrated model system that we have developed with the purpose of finding the human health impacts from air pollution in Europe, and also to find the contribution from the different sectors contributing to air pollution levels and health impacts in Europe also. So we are, with this system, asking the very big and overall questions related to air pollution. First of all, how big is the problem? What are the total impacts in Europe from all emissions in the Northern Hemisphere, both anthropogenic emissions and natural emissions? Then we are especially interested in the international ship traffic, because this sector has not been regulated very much yet. There has been some regulation of the international ship traffic in the Baltic Sea and the North Sea, where the so-called sulfur emission control area has been introduced, and I can show you the effect of this regulation. But for the rest of the area in the Atlantic Sea and in the Mediterranean Sea, there is no regulation yet. And then we have looked at the relative contribution from the 10 major emission sectors in Europe to the impacts on human health and related external cost. And the reason why we are putting cost on this is that this is the language that the politicians are actually talking. Our system is based on the impact pathway chain, which is based on that we have a specific source. This could be all sources or just only one source, like power plants. Then we are having a suite of air pollution models calculating the spread in the atmosphere and chemical transformation from these sources, giving the concentration distribution. And together with the population data, we can calculate the exposure of the population, and finding the best described and validated exposure response functions in literature, we can calculate the human health impacts. And we have around 20 impacts in the system, from premature death to hospital and all kind of different impacts. And in the end, we can put cost to these impacts. So in the end, we can tell what is the external cost from the different emissions. This is an example of one of the impacts we have in the model, namely the most important, the premature deaths. We have a very good knowledge about that. There are some premature deaths related to especially particle pollution in Europe. And with the system, we have calculated this map showing the distribution of the premature deaths due to air pollution for the year 2000. We have calculated for different years also, and for the year 2000 we found in this domain that we have the total number of premature deaths due to air pollution is 680,000 cases. However, this is decreasing to 450,000 cases in the year 2020 if we assume that the thematic strategy from the EU Commission is going into place. Also, we are compared with similar studies from the Institute EASA in Austria, and they have estimated around 300,000 premature deaths only in the EU 25 countries. We looked at the international ship traffic. As you can see, there is something, I mean, if we take it, we have to the left figures, we have SO2, which is the primary species emitted from the ships. And to the right, we have the secondary foreign particles, sulfur particles. And as you can see in the Baltic Sea and in the North Sea, from the top figures to the bottom figures are the year 2000 to year 2020. The sulfur emissions are nearly disappearing because of the regulation of the international ship traffic, where you are simply removing the sulfur from the bunker fuel in the ships. And we can see that this is really helping on the concentration levels. However, this is only happening in the North Sea and the northern part of Europe, and in the Mediterranean Sea the contrary is happening because the international ship traffic is increasing and we don't have any regulation of the traffic in this area, yet at least. When we calculated the external cost from all these overall pollution levels and the contribution from the ship traffic, we're getting some very high values. If you look at the bottom first, you can see that we have 4 different years, the year 2000, 2007, 11 and 20. And in the bottom rows of 4 rows of this table, we have calculated the total external cost from air pollution from all emission sources in the Northern Hemisphere, according to the impacts in Europe. And for the year 2000, the total external cost is 800 billion euros, which is really a lot. However, decreasing to a little more than 500 billion euros in the year 2020. We can see that in the top 4 rows, we can see that the contribution from international ship traffic is around 50 to 60 billion euros per year to the health impacts, and increasing due to increasing ship traffic in the future. And in the middle 4 rows, we have the contribution from the Baltic Sea and the North Sea, which are actually decreasing due to the removal of sulfur in the bunker fuel. The contribution from international ship traffic is actually increasing in Europe from 7% in the year 2000 to 12% in the year 2020. So this is something that has to be taken seriously. And the number of premature deaths in Europe due to the international ship traffic is lying around 50,000 cases per year, according to our calculations. Then we have also looked at the contribution from the individual emission categories in Europe and trying to see what are the relative impacts from these sectors in order to find what sectors are most important if you want to do something about air pollution and which sectors are not really important. And you can see there are 2 columns of percentages. Here we have looked at all the emissions in Europe at the same time, taking one sector out of the time. For example, the first one are the major power plants, and according to our calculations, they are contributing with 24% of the total health impacts related external cost in Europe per year. So this is really a major contributor. The second largest one is actually the agricultural sector. And this is due to the emissions of ammonia, especially from animals production. And these ammonia, when spread on the fields, are evaporated into the atmosphere and formed into secondary inorganic aerosols. And these aerosols are also included in the health impacts in the system. And of course, we then also have road traffic, which is not so surprising because we have a large contribution from this sector also. The other sectors are industrial combustion and production processes. And there are some sectors that is not so bad, namely the waste treatment sector, for example. And then we have also other mobile sources, which is relatively large. These are all the non-road vehicles used in industry and farming and so on. So the overall conclusions here is that air pollution still constitutes a serious problem to human health, and the related external costs are really considerable, even though that air pollution level has decreased a lot during the last decade and in Europe. The human health-related external costs found in this work can be used to directly compare the contributions from the different emission sectors, potentially as a basis for decision makers on regulation and emission reduction. And the reason why we're doing this is that the major and visible emission sources, for example, the power plants, where everyone can see there's a stack with a plume, does not always constitute the most significant problems related to human health. Other less obvious sector sources can cause significant impacts on human health, like, for example, the international ship traffic or agricultural sector. And in Denmark, for example, we have big problems with the wood stoves. And therefore, it is important to make this overall screening of all the emission sectors in order to create a scientific basis for sound political decisions, and not based on beliefs, but on the best available scientific knowledge in every link of the impact pathway chain. Thank you very much.
Well, good evening, good afternoon. I am Dr. Asimakopoulos from the National Observatory of Athens. I'm a researcher there. And our research is actually focused in the indoor environment, and more specifically, we monitored the air quality in the passenger cabins and the platforms of the Athens underground metro system. Now, what motivated this research? Why did we want to do it? It has been found by other researchers from other cities around the world that the underground metro systems experience really high particulate pollutant levels, well, ranging between acceptable levels or well above the EU limits set. And taking into account that people using the metro underground to move more easily around urban areas, the people numbers have increased, as well as the residence times within these underground metro systems. And in general, since these times have increased, it is thought of importance to know what levels of pollutants are they exposed to. So especially people living in urban areas experience the highest pollutant levels because of all the sources that are concentrated there. It also seems that the indoor air suffers from pollutant problems as much as the outdoor air, and in some cases, indoor air pollutants are higher than the ones we find outdoors. Especially particulate pollutants are considered to be dangerous for human health, especially if one is exposed to high levels at big amounts of time. And what are the sources in particular of air pollution that we find inside underground metro systems? These come not only from the outdoor polluted air that comes in through the ventilation systems, but also through indoor materials such as the train brake system, the tunnel linings, and other. So what we did is, fortunately for us, we captured the unusually hot summer of 2012 in Athens, where really Athens faced a series of pollution episodes, especially regarding ozone. And the temperatures were constantly above 30 degrees centigrade, and in some instances they surpassed 40 degrees centigrade. So in this really unfriendly outdoor environment, the people living in Athens used the metro to go to work or to go to their activities. The pollutants monitored are particulate matter of fine diameter, that is 2.5 micrometers, 1 micrometer. We also monitored CO2 in order to verify whether the air was renewed properly, temperature and humidity. And we captured the morning and evening rush hours for a period of 6 weeks during consecutive experiments. This is the blue line you see there is the major line, is where we conducted the experiments. And we took measurements inside the train cabins, moving from Egaleo to the Athens airport, and on the platforms of Syntagma, which is considered the most central station and is a central Athens area, and 2 suburban platforms, which is the one is on the Athens airport and the other one is on Doukisis Plakentias. What we found is that the particulate matter concentrations, especially on the platforms of the trains, were approximately 2 to 5 times higher compared to the outdoor levels, which was very interesting. And especially movement of trains really increased instantly the particulate levels, which means that air mixing is actually resuspending dust, so it gives higher levels. Inside the cabins of the Athens metro, the air quality was slightly better, especially regarding particulate pollution, mainly because most of the trains are equipped with air conditioning systems. They are of the latest technology. So air conditioning really helped in reducing the particulate matter concentrations. And it also helped in keeping a steady, comfortable temperature and relative humidity inside the cabins. However, the Athens metro is also equipped with older technology trains, which means they do not have air conditioning systems, which means people rely on opening windows in order to get some fresh air, because especially during the summer you really feel hot if it's crowded as well. And in this case, the particulate matter concentrations were 2 or 3 times higher as compared to the previous case, which means that air that was rich in particulate matter entered the cabins and also helped in reducing the air quality inside the cabins. The worst was actually on the platforms of the stations. I think because of train movement and also because the movement of people was not restricted and the volume of air was higher. And another important finding is that outdoor air quality does not, from the series of experiments we conducted, the outdoor air quality does not seem to have the same characteristics as the ones we find inside, because particulate pollution inside the underground metro system comes from the tunnel materials and from the train materials that emit particulates. Outside, in the outdoor air, we see that finer diameter particulates, that is smaller than 2.5 micrometers, dominate, which means that the sources of pollution outside are quite different than the sources of pollution inside. Now, what does this really mean for the people and for us, the scientists, is that people are exposed to different levels of pollutants regarding the microenvironments that they live in. And we should not really concentrate on the underground systems or the cabins, but we should really look, where do people live, what are their daily activities, what are the types of microenvironments they live in, and how, as a whole, we can improve the indoor air quality, not only in underground systems, but also at homes, at schools, at workplaces, and most importantly, in the outdoor air. Because especially in urban areas, the outdoor air quality is still burdened, and people are experiencing health problems, as my previous co-speaker said. And we should try and look at it as a whole and what types of measures are really needed in order to improve both the outdoor and the indoor air quality. and thus reduce further the problem of the health problems and the premature deaths.
Thank you very much for the interesting presentations. We'll now open the floor for questions. Are there any questions from the journalists here in the room? Or from those watching us remotely?
Liz Callagher from Environmental Research Web. I've got a question for Vasiliki. Where is your research being published? Has it been published?
It has been published in the form of a technical report that was handed over to the Athens transport system. It's an organization that handles the Athens metro. It has been given to them. We also gave a copy. It's my mistake, I forgot to acknowledge the financial support by the Mariolopoulos Foundation for the Environment. We also gave a report to them, a full report, and then I have a poster presentation tomorrow which presents more elaborately our results.
Thank you. And a follow-up question, if that's, how did the findings for Athens differ to the findings from other cities?
Well, the differences are not really that big. The differences actually rely on the age of the underground metro system, on the type of ventilation, on the type of trains used, new technology, old technology, and basically the Athens metro is a very new metro. It has only been operating for 13 years and it's still expanding. So it was interesting to see what are the differences between new and older underground systems, and in my opinion, the differences in particulate levels are not that big. The main difference is that we can improve the indoor air quality of the Athens metro because it's still expanding and there is room for improvement if we know from beforehand what the problems are and the possible solutions. But in other metros around the world, they have taken measures to improve the air quality. They have used newer ventilation systems or platform screen doors, and they have seen improvement.
Thank you. Are there any other questions? No? Okay. Thank you. If there are no more questions, we'll finish here. Thank you very much for coming. Thank you to our speakers. This is the last press conference of this year's General Assembly. I hope to see you all next year, both those who are here and maybe those who are watching us remotely might be interested in coming to meet us in Vienna next year from the 27th of April to the 2nd of May. Thank you. Bye.